It's been kind of a rough start to the day here. I've thought for several hours now. Today was actually Tuesday. Turns out it's really Wednesday, and who knows what day it is when you're actually watching this. So, you know, guys, I got no clue. Anyway, hope you guys are doing good. Hope everybody had a great spring break. Hope everybody had just a ton of fun, got the batteries recharged here for the home stretch. And today what we're going to do is that we're going to pick things up here with weather. We're moving along to the weather because we kind of need to start scooting through some stuff here. Weather being one of them. Now, before I start here on weather, understand again as I repeat day after day, whatever day that happens to be, that you've got to do the reading before you get here. Okay, so now, since you know that it's going to be weather, weather is going to be chapter 12 here in the FAA materials. So we're going to spend probably a 3-part lesson here on weather theory. Talking about weather, talking about earth science is what we're talking about. After that, we're going to move to chapter 13, which is going to get into some of the weather products that we use when we fly. Things that we use for our planning purposes, things that we can use en route, things that we as pilots kind of need to know. Plus, you're going to learn the secret handshake of becoming a pilot, which is learning how to decipher METARs and TAFs. Yes, this is the alphabet soup. This is all this stuff that it takes to become a pilot, is learning all these acronyms. So you're going to learn them. So remember that your assignment coming up is going to be chapter 12. Before we do that, we're going to start talking about weather in general. So in general, when we talk about weather, what do you normally think of when you think of weather? Now go ahead, take a minute, talk to yourself for just a second. Have that internal conversation. No, you're fine, go ahead. Take some time. No, you may need some time with this. Go ahead, that's fine. Hang on. Where's my microphone? That may be one of the things here. Oh boy. Hang on, guys. How embarrassing. Hold on. Boy, nothing like live TV, is there? And let's just see. Let's see if this makes this any easier to hear me. Stand by. See if you can hear me now. Is that any better? If you can hear me now? Yeah, rookie mistake. Guys, I've got to tell you, I have been out of it all week long. It has been it has been and will continue to be, I suppose, a kind of a challenging week here for me personally. So let's try this again as I ease into the chair. Now then, for those of you that were not able to read lips earlier, God, let me go back and start talking what I was saying before. Man, what a rookie. We're picking this up in chapter 12. We need to kind of move along here to get into some other things. This deals more with earth science, and that's going to be the thing that we focus on here for the next couple of weeks. We're going to be doing probably a 3-part series on weather theory, and then we're going to be getting into weather products that we use when we fly, before we fly, during, with what we do. You're going to be learning what I referred to earlier, and I don't know if you heard this or not, but the secret handshake of becoming a pilot, which is METARs and TAFs. Yeah, more acronyms. So that's what we're going to be working with. But we'll pick this up here with chapter 12. Just remember, guys, you got to read this stuff before you come to class. So your assignment before we have class coming up here on Friday is going to be you've got to read at least halfway through chapter 12. Okay. So weather theory. When we look at this, what do you guys think of when you think of weather? Yeah, just go ahead and talk to yourselves. No, just yourself, not to others. Do you think in terms of weather? Do you think like weather? Okay, we're going to have weather. Is it snow? Is it rain? Is it wind? Is it hail? Is it a thunderstorm? You know, I think weather a lot of times kind of gets a bad rap. Because really, what is weather? Often the connotation is going to be that weather is this detrimental thing. It's going to be this like bad thing. But what is it when you walk outside? It's nice and warm, calm, sun is shining, birds are singing. Isn't that weather? That's weather too. So we have what we call good weather and bad weather, and we don't really think about all the stuff in between. But the big thing to think about is that it's weather regardless. So whether or not, see what I did there? Whether or not you think that the weather is one thing or another, just understand that there is always weather. It's like when we fly. Is there going to be wind? Well, the question is not, is there going to be wind? The question is, which way is the wind blowing and how fast? That's what it is. And then we're surprised if it happens to be a calm day. So the weather is just this constant, ubiquitous thing that is all around us, and it is constantly happening to us, and we constantly make adjustments to it. So whether it's going to be cold, whether it's going to be hot, whether it's going to be windy, snowy, rainy, or just bright sunshine and just a wonderful day, understand that is weather. So then we think in terms of, where does all this weather come from? How does it happen? We don't spend a lot of time talking about, well, gosh, I wonder what the weather was like yesterday. I wonder what the weather was like last week. We don't spend a lot of time doing historical perspectives on weather, but we always want to know what's the weather going to be, right? So we want to know what's it going to be like today. That's the way most people look at weather. But we as pilots, we need to look at weather a little differently. We need to have a rolling 5-day forecast in our heads to be thinking about, what is this weather going to be coming up? Where is it coming from? Where is it going? What is likely to happen? And that's what we need to know, because we have to plan a flight. We get to the airport, we make our flight, stuff happens to us during the flight, etc., and when we land. So it's a very dynamic process. It is that rare day where we have this static weather environment. It is constantly changing. And that's one of the challenges of flight, is to say, how do we flog this airplane, this thing that I have spent all this time and money to learn how to fly, how do I do it in the current conditions? What conditions are more conducive to flight than others? Here's some good weather, here's some not so good weather. How do I know what it's going to be like later on today or during my flight? It looks bright and sunny here. Can I expect that as we move along through the next phase of our flight or at my destination? Good things to know, right? So how do we learn what that is? Well, chances are some of you have already learned some of the basics already in your science classes. This is where earth science comes from. And it's one of the things that makes aeronautics so cool, is the fact that we actually get to apply some of the earth science lessons that you learn in class. We learn to apply it when we fly an airplane from one place to another, or even just in the traffic pattern. So what we're going to talk about today is the basics. Talk about just general weather theory and kind of how things work. So in order to do that, I'm going to tap into some of your current knowledge that you may have here about weather. So here's what we're going to do. I want everybody to kind of close your eyes. Well, not kind of close your eyes. I want you to close your eyes. Okay, close your eyes. Keep them closed. Don't peek. No peeking. Okay, now then, you got your eyes closed. Now here you are. Eyes closed, everybody, eyes closed. So it is my birthday, August 15th. You can open your eyes now. I expect a card, okay? Okay, close your eyes. So August 15th, you are in Phoenix, Arizona on August 15th. It is 2 p.m. in the afternoon. There is not a cloud in the sky. 2 p.m. on my birthday, August 15th, bonus question, Phoenix, Arizona, not a cloud in the sky. what would you guess the ambient air temperature at 2 p.m. in Phoenix on August 15th might be? Now then, you're walking from a wonderfully air-conditioned shopping mall and you're walking back to your car. And a friend of yours, maybe it's a friend, maybe it's not, says to you, okay, you lost a bet, you lost a dare, whatever it's going to be, and you're going to walk up between these two cars. And what the dare has been is that you're going to place your hand on one of these cars. Got your eyes closed? I'm watching. Eyes closed. You have to put your hand on one of these cars. 2 p.m., August 15th, Phoenix, Arizona, not a cloud in the sky. You have to touch one of these cars. This one, on this side, on your right side, is white. The one on your left side is black. Which one of those cars would you rather touch? How many of you said white? You can open your eyes. How many of you said white? How many of you said black? Why did you say the white car? Why did you do that? Correct. Because lighter colored colors here in our Earth tend to reflect a lot of that solar radiation or that sunshine that you're getting in abundance on a cloudless sky in Phoenix, Arizona on August 15th at 2 p.m. in the afternoon. Yeah, kiddos, it's hot. And those cars are going to be warm. The white tends to reflect the solar radiation or the sunshine, whereas the darker colors, the black one, will tend to absorb it. And so that will, in most cases, feel hotter than the white car. Now, we don't want anybody getting burns out there, and so we don't want, people going out and trying to say, oh, I'm going to touch this hot stove. Don't do that, okay? That's not good. But this is my point. So why is it that that's hot, that this is cold, and this one's hotter? Again, absorbing solar radiation and reflecting solar radiation. It's why the lighter colors are usually the colors that are preferred in warmer climates, especially where there's a lot of sunshine, is because they tend to stay cooler. So if we think about that and we think, okay, that's the way stuff works here on Earth, can we apply that, then, that general lesson, to what happens on this big blue ball of ours? Let's find out. So, as we look here, we can see that here's a little bit of weather. If you see that little blue ball right there, that is New Orleans, and this is the weather here just to the east of New Orleans that played havoc with our internet connection here earlier today. Yeah, go Cox Cable, yay. And so with this, what we're going to do is that we're going to look at something here, and this is just the general basics of what we just discussed. Now, let's take a look at what this drawing is. So here we are. What we have here is what? This, of course, is the sun. El Sol, okay? So that's the sun. If we look down below it, here's the ocean. Let's call this the Pacific Ocean. Here is brown desert. Let's call that New Mexico. And here is Mr. Green Jeans wheat field in Kansas. Now, those of you that are not geographically impaired, you're probably looking at this map and you're saying, well, wait a minute, Mr. R, the Pacific Ocean doesn't come to New Mexico. Not yet. So, as we look at this, here we have the blue ocean, we have the brown area here of, let's call it New Mexico, and we have the green of Mr. Green Jeans wheat field in Kansas. So, knowing what we know about the colors that we talked about, which one of those colors do you suppose is going to absorb more of these rays, this solar radiation, more than the other two colors? Those of you that said brown, Reach back there, give yourself a pat on the back. Just reach, kind of reach, there you go. Okay, good job, good job. So the brown will, in most cases, absorb more of that solar radiation and actually become warmer. Okay, good so far? Now let's think about this. Whoops, see, I got the right one. Let's think about this. So we have this, and this becomes warmer. Now, what is it that we remember about warm air? It expands, right? The warm air expands because it's all about the molecule. That is correct. So the warm air expands. When that warm air expands, it can't expand down into the dirt, can it? No. So it has to expand where? Well, in most cases, it's going to go up. So when this area here of New Mexico starts heating up, that air above it gets warmer, and that warm air rises. We call this convection. Warm air rises. How many of you have ever heard of a convection oven? It's just hot air. That's kind of what it is. So we have this air that is rising. So it gets warmer at the surface, heats that air, and that warm air rises. So in relation to that warm air, what kind of happens to the air above the blue ocean and the green wheat field in Mr. Green Jean's field in Kansas? Well, relative to that air in New Mexico, this air is cooler. And when that air gets cooler, the molecules get closer together, right? And they become more dense, correct? And that air tends to fall. So the warm air rises and the cool air descends. So the same thing would happen here over this wheat field in kind of relative terms. And guys, I'm talking here in just kind of general terms here. So this is sort of what happens. Well, when this warm air rises, it creates a void. It creates a void underneath this air here over this desert part. Well, when that void is created, it has to be replaced by something. So what do you think it is? It's going to be this air that is in that transitional area between these two surfaces. And so that cool air gets pulled in to this area over the desert. And as that cool air gets pulled in by that void, again, it becomes warm and it also rises. But we also know that up here at the top, it's going to get to a certain area and it's going to start to cool as well. And when that air cools, what is that air going to want to do? Well, that air is going to want to kind of spill over here and fill in this void that was created when this air began to descend, right? So now this air gets to move out this direction, and now it starts to become cool. And now we've created this little cycle. You can see here that we've created kind of this little loop over here, and we have kind of a little loop over here. Now, these loops that we're looking at are primarily vertical in nature, and so this is just kind of one of the ways that these air molecules move around. Well, here's a question I have for you. So when these air molecules from here, from the ocean, move in here over New Mexico, the air molecules move through here to fill that void. When that happens, can we feel it? Can we feel those molecules moving? Yes, we can. And when they do move over there, what is it that we call that? Wind. That's where the wind moves. This is where an air mass can start to move. So, when we look at this, now we can see that we have some wind over here. And this is, let me just do this here. So this is where we might expect to see a little breeze coming through here. if we have this situation here and we know that there's an airport nearby, do you think this would be a handy bit of information to know with regards to what type of winds we might expect in and around that airport? That is correct. So, this is one way that this air starts to move. And it's also another way that when we look at what's happening here, I don't know why that's not happening. Oh boy, why isn't, hang on here, I don't know. Give me just a second here, guys. I thought I had this set up here. I don't know why it's, well, stand by. God, I had this all squared away and I thought this was just so cool with that, and I don't know why it's not showing. Well, okay, so much for that. Yeah, it's supposed to show the weather map, and it didn't. It didn't. So let me get rid of this. So there is, that's kind of what that weather begins to look like with regards to air moving from one place to another because of changes in temperature. So we have two big rules that happen, and these, by the way, coincidentally, are FAA test questions. Here are the rules. Number one, the sun is the source of all weather on this planet. Okay? The sun makes everything go. Rule number two, the reason that the sun makes everything go is because of the uneven heating of the Earth's surface. You're writing this down, right? Because this is solid gold here, guys. The sun is the source of all weather on the planet. Two, it is because of the uneven heating of the Earth's surface. Because of the uneven heating of the Earth's surface. Okay? Just understanding that basic concept will help you solve most of the riddles with regards to the weather. It may not help you predict things way out in the future, but it can help you understand what is happening now and perhaps what is about to happen. So those are the biggies right there. So now let's think about this a little bit more. So we think about this air rising, correct? So we think about that as rising here, which is true. But the one thing that also happens as that air is rising is that it also has a little bit of a vector, meaning that as that air rises, that air moves and it circulates counterclockwise. That air moves counterclockwise or anti-clockwise. Counterclockwise. Okay, you guys know what that is? You guys remember a clock and the hands move kind of around clockwise? This is going backwards, okay? So that warm air, as it rises, it tends to circulate in a counterclockwise fashion. As that warm air begins to rise, is there greater pressure or is there less pressure on the Earth's surface? There would be less pressure. So it would be a lower pressure then that would be occurring over that surface area because those molecules are rising, correct? Okay, so you have lower pressure circulating counterclockwise. Conversely, as the cooler air is circulating down, which way do you think it's moving? It's moving clockwise and becoming a little greater pressure. So we have lower pressure going up, circulating counterclockwise, we have higher pressure moving down, circulating clockwise. Okay? Good so far. So now we know kind of how this uneven heating can create not just vertical movement, but it can create also directional movement around these areas where this air is rising or falling. So we keep that in mind here as well. Good so far? Okay. Those are kind of the basics that I just wanted to share with you, just so that you had a kind of a grasp of what it is that weather does, where it comes from, the fact that it's not all bad, that there is equally good weather is equally to what we call bad weather. It's just weather. Good or bad, it's weather. Okay? So that's the big thing that I wanted you guys to be aware of. Now then, getting into chapter 12, into weather theory. Pardon me whilst I sip. Okay. So as we look at this now, we're looking here at kind of the basic weather theory. This is the chapter that I want you guys to read. And so as you're looking at this, one thing here, guys, that I want you to be aware of is that the weather, by and large, can be it can be one of those things that some people find a little boring. And I know that when we start talking about weather, and this is oh, hang on, goodness, I don't know what I just did. I just messed this up again, guys. I'm sorry. I was trying to fix this. There we go. And it can be a little bit boring, I think, to some. And I have to tell you is that I really didn't have a real good, I really didn't have a great appreciation for weather until I really started flying on instruments. Once you start flying on instruments, your appreciation for weather is huge. And it was one of those things, it's like I kicked myself and I said, my goodness, why didn't I pay more attention to this whole weather thing? So there were some things I had to kind of relearn, if you will. And what that means is that I actually had to learn it. So that's when you really start developing an appreciation for earth science, for the weather, is when you're having to fly an airplane in it. So this is why this stuff is kind of important. As a ground instructor, with all of this, one of the things that we always used to dread is how do I teach people how to use non-directional beacons and an automatic direction finder, teaching bearings and relative bearings, because you had no frame of reference to show people, because you almost could not find these instruments in airplanes anymore. Well, a couple of years ago, the FAA finally did away with asking those questions. Thank goodness. So the second piece came in having to do with the weather. And it's that weather piece that all instructors, we sit here and think, okay, I just need to try to hold this class together through this weather thing without everybody going to sleep. So I understand, guys, it's kind of boring, especially to you right now, but I can promise you, it is going to be one of the things that you are going to wish you knew more about once you start flying. So just try to keep that in mind as you go along here. So with this, we look, does that loop kind of look familiar to you here, right there? Okay. We look at our atmosphere. We look at this. These are things, guys, that you already know. Remember, the Earth, our gases here in our atmosphere is 78% nitrogen, 21% oxygen, 0.9% argon, 0.1% everything else. Test question: 78% nitrogen, 21% oxygen, 0.9% argon, 0.1% everything else. So that is the composition of our atmosphere. This is all molecular, because we all know it's all about the... So, when we look at our atmosphere, we can see that we have several layers. The troposphere is going to be one of the lower levels here, and it kind of goes here to approximately 20,000 feet MSL. Stratosphere is going to be above it. The mesosphere, the thermosphere is going to be above that. The big things that we look for here is we look for the weather here in the troposphere and in the tropopause and in the lower stratosphere. Those are the things that we are primarily concerned about here on our planet. Now, another thing that we talk about circulation patterns in kind of a static environment, meaning that it's not moving. So we know up here at the poles, what kind of air do we have up here at the poles? Well, we have kind of cold air, right? We have cold air. What kind of air do we have down here around the equator? Well, we have warmer air, right? So what do we know about that cold air based on what we just talked about? That cold air, molecules closer together, they get heavier, and what do? Right? They tend to move down. Well, this air, then at the equator, it gets warmer and it tends to rise, right? And then it kind of circulates up here. So you can kind of see this loop action that we're talking about, these things. This is kind of the way that it works. The difference is going to be is that actually here, instead of this static element here, is that we know that this big blue ball of ours, it actually spins so that the Earth moves, it turns. So we have not just the tendency for the air molecules from the poles to move toward the equator, and then they warm, and then they go up, and then they move back toward the equator, or to the poles on a higher trajectory, creating these loops. But we also have the Earth that spins. That tends to create this friction in the molecules and tends to pull this air with it. So we have not just descending and ascending, but we also have movement from left to right. Okay, in most cases. Sometimes that can back up and come the other way, not the Earth, but the weather. So we look here, the things that I want you to be aware of is to understand what the troposphere is, what the stratosphere is, and what the tropopause is. Okay, so as you look here, you can see here where the tropopause, and in your reading you'll understand kind of where that is. The Coriolis effect, that is that thing that we talk about when we start throwing in a little spin into the thing. We look here on the illustration here on page 12-4, and this illustration here shows that at sea level we have approximately 14.7 pounds per square inch is what our atmosphere weighs. And up at 18,000 feet, we can see that the atmosphere, it gets down to pretty much half of that. So at 18,000 feet, which is going to be the base of class alpha airspace, is that the pressure exerted on the Earth is about half of that atmospherically as opposed to sea level. Because we know that down in Maui, that's where all the molecules live, right? Because, you know, they're at sea level. At 18,000 feet, it's approximately half of that. So keep that in mind about how those molecules expand, you know, as they go up. Then we also look here at the Coriolis effect in the circulation patterns. This is due to the rotation of the Earth. So for instance, if we remember this illustration here, which is just kind of a static thing if the Earth didn't rotate, but because of the fact that it does, it creates 3 of these loops, each in the northern hemisphere and in the southern hemisphere. And this is kind of where these circulation patterns develop. So we can see that from the equator to about the 30-degree mark here in the parallel, which is kind of lower here, it's kind of just a little bit north of New Orleans, in fact, down here, is that you have this loop circulation pattern that is, again, all of this is general, but is generally in effect Then you have up here from about 30 degrees of latitude up to 60 degrees of latitude, you have another band that circulates. This one kind of comes up and out and down. This one comes up a little bit differently, where you kind of have that cooler air circulating here. And then you have up top here in the Arctic Circle, you have another loop. So keep in mind that you have these weather makers in various locations here in the various latitudes. So normally here at 0 or the equator, 30 degrees north and 60 degrees north, and they're going to be the opposite here in the southern hemisphere. The reason I bring this up is because it really complicates things when it comes to predicting weather. It would be great if everything were just kind of static and it didn't affect anything here. This one here, I'm not going to say unfortunately, because having the Earth spin is a good thing. But with this is going to be a thing that complicates things with regards to weather. So just keep that in mind. Measurement of atmospheric pressure. Remember that we do it by inches of mercury. So we look here, here's this vat that we talked about, and at sea level here with approximately, on a standard day, 14.7 pounds per square inch, that would push approximately 29.92 inches of mercury up into this tube here, this either a Torricelli tube or whatever you want to call it, on a standard day. So this is kind of where this goes. The thing that we need to remember is this. What is it that creates a standard atmosphere or a standard ISA? This is something that we've talked about. We know that at 15 degrees Celsius and 29.92 inches of mercury, that is what we define as a standard atmosphere. Anything colder or warmer than that is non-standard. Higher pressure or lower pressure from that is non-standard. But that's where we set the bar. And by the way, the equivalent, the millibar equivalent to 29.92 inches of mercury is 1013.2 millibars or hectopascals. Hectopascals. You can write that down there. 29.92 inches of mercury equals 1013.2 millibars or hectopascals. I always feel so cosmopolitan when I say hectopascal. So that is going to be what we call the standard atmosphere. Okay? Remember how, when we looked at instruments, how those work. Higher pressures pressing down on this aneroid wafer here, or this aneroid barometer, creates a linkage here that shows a higher pressure. So the more atmospheric pressure that we have pressing down, it shows the higher pressure here. And the less pressure that we have, this aneroid wafer expands, and it shows that we have a lower pressure. Remember, that's kind of how the altimeter works. You guys remember that? I think you do. So let's look at the difference between what the actual pressures themselves would be here in between New Orleans. Isn't that cool that they actually show New Orleans on here? And Denver. So here we have, on a standard day in New Orleans, it's going to be 29.92 inches of mercury at 15 degrees Celsius, which is approximately 59 degrees Fahrenheit. Some people will round that up a little bit to 60 degrees Fahrenheit. Well, there you go. And when we look at Denver, we know that the equal pressure in Denver, which is a mile high, 5,280 feet, is that that pressure would relate to 24.92. And what that means is that we lose approximately 1 inch of pressure per 1,000 feet. So we lose 1 inch of mercury per 1,000 feet. The other thing that happens is we also lose 2 degrees Celsius per 1,000 feet. So keep that in mind. So where this would be 15 degrees Celsius here on a standard day, what would it be here in Denver? Well, remember, it's 5,280 feet. Let's round that off to 5,000 feet. So if we say that we have 2 degrees Celsius per 1,000 feet, how many have we lost? We've lost 10, meaning that here a standard day in Denver would be approximately 5 degrees Celsius, okay? So keep that in mind, that that's sort of how that works. Good so far? All right, that's the end of part 1. And I'll be getting part 2, and we're going to pick that up right here where we left off here in Denver. Huh, who knew? Talk to you later, guys. See ya.